Good afternoon to all. This is the tutorial session for NPTEL course Thermal Engineering Basic and Applied. So this is a graduate level course or an undergraduate level course taken by students of both these courses. And we will see in this subject a few cycles, Otto cycle, diesel cycle, and the review of all the thermodynamics that we have seen in the basic thermodynamic course, and a bit more deeper topics as we go further down the course. My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. In this week, actually, we will see a few multiple choice questions and problem solved, numerical type problems based on the first week lectures uploaded in the course website. The main contents are a review of thermodynamics, basic thermodynamics, the other course that is offered in NPTEL, and then first law. If you go into the contents of this, first law for closed and open systems and second law systems, and the tutorial problems that we see in this session can help you to solve the assignment questions of the that is uploaded in the course website for this week. You can interrupt in between if you have any doubts regarding the problems that we will be solving. We can actually have a kind of a discussion about the problems that we will be solving today. We can move into the questions that we have for this week. Look into this. So it's a multiple choice question. It's a basic question. You can
option A.
Yeah, option A. Yeah, right. Yeah, let's give time for the others as well to look into it, and I'll try to solve it then. Give me a second. Let me change the view of a slideshow in my monitor. I'll just log out and log in within a minute.
Sir, what is the score required for join MTech in thermal and fluid in IIT Delhi?
Last time, depending upon their reservation and the
In
category
general.
general, yeah. Last time people with somewhere around score 690 and all got from general category.
Out of
690 and
100,
so
sir? Out of
out.
100?
No, it's a score that matters, right? It's a gate score is valid for 3 years. So if the score that you get in the previous year is based on some mark, that will not be the score you'll be getting for the same mark this year. So in order to have a normalization, they'll take the score into consideration.
Sir. Out of 165?
That should be that depends upon the year actually. So in my times, 78 and all somewhere around that was required to get into IIT Delhi Thermal. Now actually the exam has become very tough. So I guess somewhere around 60 would be sufficient, I guess 60, 65. But that's again, that's relative. You need to look into the score as such. Is my screen visible? The shared
Yes, sir.
screen. Okay, thanks. So yeah, the answer is right. It's option A. I'll try to solve it how exactly it will be getting that. So this one. Yeah. So the answer is option A. The question says a heat pump is operating between a source of temperature T1 and a sink of temperature T2, and says that higher the source will be obviously at a higher temperature than the sink temperature, so T1 greater than T2. A refrigerator is operating between the same temperature limit. If the coefficient of performance of the heat pump and the refrigerator are COPH and COPR respectively, then relation between them is which out of the four options? It's very straightforward. We have to draw the schematic for the heat pump as well as the refrigerator that operates between the same temperature source and sink. T1 is a higher temperature source and T2 is the lower temperature. sink. So a heat pump takes in heat from the high temperature source and releases and produces work, and consider this to be a reversible one for the time being. And in the case of refrigerator, it takes in heat at the lower temperature sink and then delivers it to a higher temperature source by taking in external work. So in this case, these two are the things, but this is a case of a heat engine. And this is the refrigerator. And then there is a third thing called heat pump. Basically, that is the refrigerator that operates in the refrigeration cycle only. But then the only difference between a refrigerator and the heat pump is that the desired energy, the desired effect that we get out of these two are different. In the case of refrigerator, the desired effect is the heat taken from the lower temperature source. That is basically sink. But meanwhile, in the case of heat pump, the heat provided to the sink, in this case, it is a higher temperature source, a higher temperature region, that will be the desired effect. So we define COP, that is the coefficient of performance, as the desired effect divided by the amount of power input. So what we could see is that COP of refrigerator is equal to the desired effect, that is Q. If you say this as Q2 and Q1, COP refrigerator will be equal to Q2 divided by work. COP heat pump will be equal to Q1, that is a heat delivered to the higher temperature divided by the work. So if you are considering a reversible ideal heat pump as well as a refrigerator, we can actually write this heat transfer rates, the ratio of the heat transfer rate in terms of the temperatures of the source and the sink. So in the case of refrigerator, we can write in terms of the temperature of the lowermost point, that is T2, and the work done, input to the system. So that could be written in terms of Q1 minus Q2. So that Q1 minus Q2 could be represented in terms of the temperature straight away. So you can write it as T1 minus T2. And for the heat pump, it reverses. What we need is the desired effect is the heat delivered to the T1. So that will be the source. That's basically sink, but at a higher temperature. So that will be at a that temperature you have to take straight away, and then the work input will be same as T1 minus T2. So basically, what you could you could see is that COP of the refrigerator will be somewhat related to the COP of heat pump. Only the numerator changes. So in order to bring an equivalence, you can say that COP of heat pump is equal to T1 divided by T1 minus T2 plus this is the same, and the COP of refrigerator is T2 divided by T1 minus 1. So you can rewrite this as T1 minus T2 plus T2 divided by T1 minus T2. So the first term will be 1, taking the T2 divided by T1 minus T2, that is same as that of COP of the refrigerator. So you'll get the first option. Operating a heat pump and a refrigerator operating between the same temperature limits, we can say that the COP of heat pump will be 1 plus the COP of the refrigerator. So that's option 1. Any questions?
No, sir.
Now we can move into the second problem. So it's a question that is based on the reversibility of a cycle. Look into it and see whether this is a possible cycle or not. Reversible or irreversible or impossible. Just check into it, and I'll also try to solve it in a couple of minutes. Okay, the question says is you have got 200 kilowatt heat supplied to the heat engine at a constant temperature source of 600 Kelvin. It rejects 700 kilowatt of heat at 300 Kelvin. Which of the following statement is true for this heat engine? It is a reversible cycle, it's an irreversible cycle, it's an impossible cycle, or the efficiency of the cycle is greater than 50%.
The impossible.
Yeah, right. How did you arrive at this solution?
Efficiency equal to heat supply minus is rejected by heat supply. Then it comes out to minus 2.5.
Uh, beg your pardon, there's a small correction. This is 1200 kilowatt. This is 1200. Beg your pardon, there's a small correction. This is 1200 kilowatt supplied to a heat engine at a constant temperature of 600 Kelvin. It rejects 700 Kelvin at 300 Kelvin. 700 kilowatt at 300 Kelvin. Yeah. So this is a small correction. This is 1200 kilowatt.
Irreversible cycle.
Yeah, right. How did you get it?
Sir, efficiency comes out to 41.66%, and by Carnot efficiency, it came out 50%.
Okay. So you know,
So
right, how to check.
less than Carnot efficiency.
Right. What we can, so the answer is right, it's an impossible cycle, but the option 4 is kind of different from the first three. So the first three, you have to check the reversibility of the cycle or the whether the possibility of the cycle is there or not. For that, you have to check into the cyclic integral of the d cube divided by t. That is the heat transfer rate that is happening at a source or sink temperature. You have to take that into account, and you have to calculate for each and every heat transfer that occurs within the cycle. So currently you can draw the temperatures, two temperatures, that is 1000 the 600 Kelvin, and the lower one is at 300 Kelvin, and you have a heat engine operating in between, and it takes a heat of 1200 kilowatt and delivers a heat of 700 kilowatt to the lower temperature reference, that is the sink basically. So what we can try to do is that we can calculate the cyclic integral of dq divided by t for this cycle, and with respect to the cycle, the amount of heat that is input will be taken as positive, that is 1200 kilowatt divided by temperature is 600 Kelvin, and then the amount of heat rejected out of the if you take a control volume over the heat engine, that will be equal to minus 700 kilowatt, and it is delivered to 300 Kelvin. So when we calculate this particular,
minus 1 by 3.
yeah. So it will be a minus of 0.33, and this will come to less than 0.
0.
So
it violated the entropy principle.
Yes. That's what they say. So if this particular quantity dq by t is less than 0, that it's an indication that the cycle is an that's an indication that cycle is impossible. Sorry, it's an irreversible process. So cyclic integral of dq by t equal to 0. That means that it's a reversible cycle. Cyclic integral dq by t less than 0. That means that the process is an irreversible cycle. The cyclic integral dq by t greater than 0. Impossible cycle. So the option to this is it's an irreversible cycle. So option B is right. But then the final option on this question says that the efficiency of the cycle is greater than 50%. So you need to verify that based on the first law efficiency. That is, the efficiency first law could be stated as heat supplied minus heat rejected, basically the work output of the cycle divided by the heat supplied. So that is 500 divided by 1200 is less than 50%. So this option is also wrong. So that gives us the right solution, that is option B. It's an irreversible cycle. So basically you have to take into consideration this cyclic integral of dq by t for these cycles. This is based on the second law. And if it is less than 0, it's irreversible, equal to 0, reversible, and greater than 0, it's impossible.
Clear, sir.
Okay, any questions?
No, sir.
We can move to the next problem. It's answer, please. Yeah, it's a numerical problem. Look into it. It's based on a piston cylinder device. It's first law based consideration. You have to take into it's a constant. It's a closed system case. So just look into it and try to solve it. Meanwhile, I'll also try to solve it in another 1 minute.
$55.45 kilojoule.
Right. How did you arrive at the solution?
Sir, P1 ln P2 by P1.
Yeah, right. Yes. So this is a case of a piston cylinder device. Initially contains 0.4 meter cube of air at 100 kilopascal and 80 degrees Celsius. The air is now compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. It's an isothermal process. Determine the work done during the process. It's a straightforward problem that needs to be solved using the equation straight away. So piston, air inside it initially was at 0.4 meter cube and it's compressed to 0.1 meter cube. T1 remain equal to T2. And this is V1, V2. Initially the pressure was 100 kilopascal and initially the temperature was 80 degrees Celsius. So it remains the same throughout. We need to determine the work done during the process. So it's a constant pressure process, it's a constant temperature process. It's an isothermal process that can be represented in the PV diagram as 0.4 and 0.1 and initial pressure 100 kilopascal and final will be obviously a higher pressure. So for an ideal gas, here it is air at constant temperature. PV can be written as a constant. So work done is equal to, it's a closed volume process. It's a closed system process. So can be written as P into TV. Integral of 1 to 2 PdV. So if it is an open system, we would have written work done as minus of integral VdP. So it's a closed system, therefore we have to write as PdV. Pressure is actually dependent upon the volume used in this equation. So you can write pressure as constant divided by dV divided by V. So this actually can be integrated from process 1 to 2 and you'll get V work done as 1 by V can be integrated as ln of V2 by V1 and the constant that comes outside, that is PV, that's equal to PV. We can take a PV at a first point or the second point. So for the time being, since we know the pressure and the volume at the first state point, we can write it as PV1 ln of V2 by V1. So we can denote it as 100 kilopascal into 0.1 meter, 0.4 meter cube multiplied by ln of V2 divided by 8. So you'll get the answer as minus of 55.5 kilojoule. This minus indicates the work is done on the system during isothermal compression. Work done. Okay, that answer is right. Now we can actually move into another problem. So this is also a numerical type question that works on the piston cylinder, but it has got a spring as well. I'll look into it and try to solve it. Were you able to solve this problem?
No, sir.
Yeah. Then we'll discuss. So this is a case of a piston cylinder device. It contains 0.05 meter cube of a gas, initially at 200 kilopascal. At this state, a linear spring that has a spring constant of 150 kilonewton per meter is touching the piston but exerting no force on it. So if I try to draw it, so there is a piston and a spring that is connected on the other side to the side where there is gas. The cross-sectional area A is 0.25 meters squared. And at the first state point, the spring is not at all compressed. It is just touching the piston. The initial pressure is 200 kilopascal and volume is 0.05 meter cube. So at the state, a linear spring that has a spring constant of 150 kilonewton per meter is touching the piston but exerting no force. Now the heat is transferred into the gas, causing the piston to rise and compress the spring until the volume inside the cylinder doubles. So initially it was 0.05 and finally it will become 0.1. The new point V2 will be equal to 0.1 meter cube.
So
If
320
the
final pressure. 320
right,
kilopascal.
right. That's right. So we'll try to solve it. And if the cross-sectional area of the piston is 0.25 meters squared, we have to determine the final pressure inside the cylinder, the total work done by the gas, and the fraction of the work against the spring to compress it. For this, the pressure exerted, we need to actually calculate the pressure exerted by the spring on the gas over the piston. And that plus the initial pressure will be equal to the total pressure inside the cylinder. So initially what we have told is that initial pressure is 200 kilopascal when the spring is just touching the gas. So we can denote P1 is 200 kilo Pascal, and we need to calculate P2. That's the first part of the problem. So we can denote the process in a PV diagram, PV plane, PV. The initial pressure is 200 kilopascal and final pressure is P2 and we need to determine it. So initially the state point B1 will be 0.05 and final state point will be equal to 0.1 meter cube. So this is a linear spring. That means that the pressure, you can denote the force in terms of spring constant as well as the displacement that happens to the spring. So in this process, since this is a linear spring, you can say that the pressure varies linearly with respect to the volume. So you can denote it straight away like this. First process and the second process will be like this. So you can calculate the second point will be at 0.05, point will be at 0.1 meter cube, and the pressure we need to calculate somehow. We will try to look into how we can get it, the pressure of the 0.2. First of all, we need to calculate the displacement of the spring. the only information right now we are having is the change in the volume. But we can actually get the change in the volume. We can actually transform change in volume to the change in length of the spring using the cross-sectional area. This is a cylindrical, this is a cylindrical domain, right? So the volume will be equal to the cross-sectional area multiplied by the length. The cross-sectional area is a constant of the piston, that is 0.25, and the length, the change in length could be directly transformed from the change in volume. So the change in length delta x of the spring is given by the change in volume divided by the cross-sectional area. That is 0.1 minus 0.05, 0.05 divided by cross-sectional area is 0.25. We'll get it as 0.2 meters. And once you get this, it's easy to get the force exerted by the spring in the final state on the piston. So if you know the force, you can calculate the pressure divided by when you divide the force by area. And the idea behind doing this is we need the final state point P2. So we calculate the force exerted by the spring when it is at the final state. F is equal to Kx 150 kilonewton per meter into 0.2. This is given 150 and 0.2 is the displacement of the spring, so you can get it as 30 kilonewton. And then we can calculate the pressure corresponding to this force, pressure corresponding to this spring force is equal to force divided by cross-sectional area. So that will be 30 kilonewton divided by 0.25 meter square. That will be equal to 120 kilopascal. Now we know the pressure exert corresponding to the spring force in the new state. And the initial pressure was 60 exerted by the gas onto the piston surface. Since this is a linear spring, and it is a compression process, the final pressure will be a linear variation. So straight away you can denote the final pressure exerted by the spring or the final pressure that is present in the gas or exerted by the spring piston on the gas will be equal to the, can denote the spring force by PS, spring pressure by PS plus the initial pressure. So this initial pressure was 200 and the final pressure is 120. The spring piston is 120. Initial spring piston was 0. So that will give you 320 kilopascal. So this is the final pressure inside the cylinder. That is the pressure exerted by the spring plus piston assembly onto the gas or vice versa. That is 320 kilopascal. Pressure is always compressive.
Sir, can we find the work done against the spring to compress from the area under the PV diagram on projected on volume axis?
Yeah, you can. So it has got two components, right? So one component is the fraction of the work done against the spring. So that happens from 20 to from the first state point to the second state point. And then there is a constant pressure term. So the bottom rectangle. So this bottom rectangle term
Otherwise,
is
sir,
always present.
we can find out from area of trapezium half of sum of parallel set into distance between them.
Yeah, you can. It's from this trapezoid, you can, the area that is present under the line when it is projected onto the x-axis, that will give you the total work that you can do it. But that's the second part of the problem. We can, that's the way we can do it. And then there is also another term that you have to calculate, that is the fraction of the work done against a spring to compressive tension. Basically, there are two parts to it. Yeah, you are right. The second part of the problem, total work done by the gas, we can calculate by the area of the trapezoid, or the area that is projected by the line onto the x-axis. So yeah, work done. So we can actually denote it by a different color. So basically, this will be the area under this trapezoid denoted by the green color. This will be the total work done by the gas. So this will be equal to half into
P1 plus P2 into V2 minus P1.
Yes, right. So this is a area for the trapezoid. So you add the parallel components and multiply it with the vertical distance, the perpendicular distance between the two parallel edges. So this is how you calculate the area of a trapezoid. And this will be equal to 320 plus 200 kilopascal multiplied by delta V is 0.05 meter cube. So this will be equal to 13 kilojoules. And the slightly confusing part of this problem is the last part. We have to calculate the fraction of the work done against the spring to compress it.
Half kx square.
Yes, right. So the potential energy that is stored in the spring during the compression process can be written as half into spring constant into the x squared, delta x squared, or basically x2 squared minus x1 squared. But also it could be determined in a different manner. Basically, that is equal to the area that is the area of the triangle that is subtended between these two endpoints. So basically, this top triangle area. That is that is also the same. In either way, you can calculate the work done against a spring to compress. It's a linear spring, basically. So we can write it accordingly. Work done by the system or the gas against the spring the first way half k into x2 minus x2 squared minus x1 squared, the change in potential energy of the spring. That's a straightforward method. We know everything, so we can write it as the initially the final length will be 0.2. Initially, it was mentioned that the spring just touches the gas. The spring piston cylinder just touches the gas, such that it is not having any compression at all. So initially, it will be length will be 0. The final length of the compression, that will be equal to 2. So 2 squared minus 0 squared, that will be equal to 0.04 equal to give us 3 kilojoules. And this can also be determined by the other method, that is the area of the triangle subtended between the line, subtended between these two lines as well as the process between 1 to 2. So that will be equal to half into the pressure is 320 minus 200 multiplied by the change in volume delta 0.05 meter cube kilopascal. So that will give you the same as 3 kilojoules. So these two are the two methods in which we can calculate the work done against the spring.
Can we say the isobaric work done is around 10 kilojoule?
Constant volume.
Isobaric.
Yeah, yeah, constant pressure. Yeah, a constant pressure will be this one 200 multiplied by this change, right? Yeah, V2 minus.
10.
Yeah, I can say that.
Totally 13, and spring compression takes 3 kilojoule. Then the remaining is 10.
Yeah, right.
Okay, sir. Okay.
But it's mentioned right in this process. It's not isobaric.
Not
So yeah, it's just the previous one was isothermal, and this is like a constant. An additional compound is involved. The spring compound is involved. This is neither isobaric nor isochoric. Means there is a change in volume as well. Yeah. So in this problem, this is a continuation from the previous problem where we an additional component of spring is there. We need to calculate the total work done against the spring and the total work done in the process as well, and also the final pressure of the gas. So the final pressure of the gas is slightly ingenious to get, because you can straight away get it from, since it's a linear spring, you can actually get it from the change in the volume, and from the change in volume you calculate the distance traveled by the spring, and then you multiply it by the spring constant to get the force, and from there divided by the cross-sectional area of the piston cylinder, you'll get the pressure exerted, new pressure exerted by the spring on the gas cylinder assembly on the gas. So that plus the initial pressure will be giving you the final pressure.
Okay, sir.
Yeah. So any questions on this this particular problem?
No, sir.
Anyone else? Any doubt? No. Okay, then we can move into the next problem. This is also a numerical problem. It's a straightforward one. It's a system. Just look into it. Check whether you need to use steady flow energy equation or any other equation in this case, or you can solve it in some other manner.
Sir, figure A, where is the?
Oh, for the figure. Sorry. I'm sorry. This is a case of an adiabatic steam turbine. Adiabatic in the sense there is no heat transfer in this process. There is no heat transfer that happens with from the control volume to the surroundings in this process. And it generates a power of 5 megawatt, and the inlet and exit conditions as given in this figure. Figure A, we need to compare the magnitudes of enthalpy H, kinetic energy Ke, and potential energy Pe. And we need to determine the work done per unit mass of the steam flowing through the turbine and the mass flow rate of the steam. So the condition of the steam at the inlet of the steam turbine is 2 megapascal. Pressure is 2 megapascal. Temperature is 400 degrees Celsius. Velocity is 50 meter per second, and the altitude set is 10 meters. And at the outlet of the steam turbine, it is at 15 kilopascal. And the quality of the steam, basically the dryness fraction, amount of vapor divided by the amount of vapor plus the total sum of the vapor plus liquid that is available at the exit of the steam turbine, that is 90%. Velocity is 180 meter per second, and the height is 6 meters. We need to calculate basically work done and all the magnitudes of the enthalpy, kinetic energy, potential energy, and the mass flow rate of the steam. We know the total power output from the steam turbines is 5 megawatt. So if we can calculate option B, the work done per unit mass of the steam flowing through the turbine, then based on this 5 megawatt, you can calculate the mass flow rate. Basically, you have the inlet properties, outlet properties. You need to calculate uh, the other property values, enthalpy, and the energy values as well, kinetic energy and potential energy. This is not straightforward because you will require a steam table for this purpose. I can give you the values for the corresponding enthalpies that we might encounter in this problem, and using that we can actually try to solve it. So how can we draw the process in a TS diagram, TS plane? This is a constant. It's an adiabatic expansion of the steam in a turbine. So if you try to draw the vapor dome, it can actually be like this. If you assume this to be a reversible adiabatic one or the isentropic process, it can come from point 1 to point 2. For an isentropic So initially the point 1 will be at maybe pressure 2 megapascal and temperature 400 degrees Celsius. And this state point 1 can be denoted as a superheated condition where the vapor will be in a state point where where the incoming steam will be only in a state point where only vapor will be there, and this vapor will be at a temperature very much higher than that of the saturation temperature at the constant pressure. So if you denote the heating process, that should be in a constant pressure process. But in that process, the temperature increases. So this particular state point at the end, that will be the saturated vapor form. And what we have at the input of the adiabatic turbine, that is at a temperature significantly higher compared to the saturation temperature, that is this particular line. So this state point is called a superheated condition. And once it expands in the turbine, it comes out of the turbine in the form of, in a two-phase condition where a part of liquid, there will be a presence of a liquid as well as vapor. And but we to denote that particular point where exactly it comes, we need to have an additional property, that is the dryness fraction. A simple temperature and pressure won't be sufficient for a state point within the vapor dome, because a temperature will be corresponding to a pressure for the saturation condition. They can't exist without one another. They will coexist. So in order to denote the state point, you need another property, and for that we use the dryness fraction or the quality. Both are same of the vapor that is coming out. So 90% vapor corresponds to vapor quality or the dryness fraction that corresponds to mass of vapor divided by mass of vapor plus mass of liquid. So this is an additional state point that will help us to determine this particular point, and from there we can calculate the other properties like enthalpy, specific enthalpy, and entropy if required, and the other terms. Try to solve it. I guess these points will be sufficient, but in order to calculate the final value, you will be requiring the steam table to obtain the state point values. So yeah, the state point one, it will be having pressure of 2 megapascal, temperature of 400 degrees Celsius. That's pretty much enough to identify the state point. So we can calculate it. I am not showing the steam table as such in this case, but I am using a software to determine it. You can use a standard steam table that's available from in the market, the academic that is used in the academy. At inlet, state point one, steam is in superheated condition. So you go into the superheated section of the steam table and use the pressure 2 megapascal and temperature 400 degrees Celsius to get the specific enthalpy H1 3248.4 kilojoule per kg. In this case, we need not require the entropy as such because every state point is straight away known. If there was a case where it was mentioned that it was an isentropic or a reversible adiabatic turbine, then we can calculate the specific entropy at this particular point. And since this is isentropic process, the exit point will also be having the same entropy. So if you have and we know that this might be within the vapor dome as well. So if you know some other property like a temperature and the entropy, we can calculate the quality from that straight away. Since the quality is given in this problem, you need not worry about the entropy in this case. And we also do not know whether this follows a straight line. This is for a representative purpose that I had drawn that this might be a case of a isentropic reversible case, but state points are already defined in this problem, so it's a straightforward problem. At turbine exit, it's saturated liquid vapor with a quality of 0.9. We can denote the enthalpy at that particular point as the fluid enthalpy plus the dryness fraction into enthalpy of vaporization at the temperature or the pressure. The saturation, yeah.
At the dryness fraction 0.9, it should be wet before.
No, dryness fraction 0.9 means that vapor content, the mass of the vapor will be having 90% of the total mass.
Then it is not saturated liquid. It is within the vapor dome.
Yeah, it's within the vapor dome, but
Then
we need to
liquid
determine
wet vapor state of the vapor, sir.
can you repeat the question again once again?
At the turbine exit two, state point two lies do not lies in a saturated liquid vapor line. Na?
It doesn't lie within.
It does not lie on the exact on the saturated liquid vapor. Acha,
No, it
saturated
yeah.
liquid vapor equal to wet vapor, sir.
No, I'm not. Yeah, I guess it doesn't lie on this particular line. This
Within
row.
the
It
vapor
doesn't lie.
dome.
It doesn't lie on the saturated vapor curve.
Hmm.
It will lie within the vapor dome, saturated
Uh,
vapor dome. So or vapor dome. In the vapor dome, it will both the vapor and the liquid coexist. So this is
then
saturated. So this left curve is called saturated liquid, and the
liquid
right
line
hand side is called saturated
saturated
vapor.
vapor line.
So it can lie in between. So that particular point can be denoted by a second property called the quality. So maybe at this temperature and pressure, if the quality is 1, that will lie at this particular point. If the quality is
Saturated
0, it will lie here. If it is
uh,
9, if it is 0.9, it will be more towards this saturated vapor curve.
vapor.
So
Okay,
that's
sir.
how we determine the enthalpy.
Okay.
So at this temperature of at this pressure of 15 kilopascal, you'll get a corresponding saturated. This is a saturation pressure, this 15 kilopascal. So at this pressure, you'll get a saturation temperature, but we do not require it. From the saturation pressure itself, we can calculate using this quality. You can calculate the enthalpy corresponding to the point 2. So at this pressure, at this saturation pressure, you can calculate the enthalpy of the fluid and then enthalpy of the vaporization from the steam table. I'm using a software for that. I get it directly, but you can look into the steam table to calculate these two parameters and substitute and get the value of H2.
H2. Okay. Sir,
So
if
HF,
temperature and pressure both are given means by what property we consider like
no,
in
temperature,
inlet.
yeah, so inlet.
P1 and T1 both are given
So
by
yeah, so
either
this,
temperature
yeah,
based or pressure based.
uh, yeah, I'll come to it. So the point 1 is called the superheated region. So here this state of the steam at the inlet of the turbine is superheated. That means that it will be purely vapor. So it's a single phase thing. So you know the Gibbs phase rule, right? If there is only a single component and two phases, how many properties are required to define the state point?
One.
G plus F is equal to C plus.
Must be equal to C plus 2.
Check it. One state point. No, one phase. And
Components.
components is steam, H2O1, right?
One. And then then two property. F equal to 2 degree of freedom.
Right. So degree of freedom is 2, right? You require two properties to define a state. Okay, so it can be pressure entropy, it can be temperature entropy, it can be pressure temperature, or a pressure specific volume, or temperature specific volume. Whatever be the combination, you require two properties. Now in this particular problem, it's straight away given. You have pressure and temperature. You require both of them for the state point 1. Right? Similarly, and when it is in two-phase condition, you require an additional state point. Pressure and temperature can't coexist as such. Because a saturation pressure corresponds to a single saturation temperature within the vapor dome. So if, for example, if this is a straight line, at every point in the straight line, pressure and temperature will be the same within the vapor dome. And here, another pressure and corresponding to another temperature. Like that, if you vary from one point to the another, the pressure changes and correspondingly temperature changes such that there exists only a single pressure or a single temperature. So within this particular line, it won't vary as such. The reason for that is that we are, in most of the cases, we are considering constant pressure processes. So, so if, for example, in the case of a Rankine cycle, if there is a condenser, the heat rejection process will be considered a constant pressure process. It moves from here to here. So the pressure remains the same, and only the quality of the steam changes in this process as it moves from the right hand corner to the left hand corner. It's a saturation condition. A pressure remains at constant at the same temperature. Consider the case of 100 degrees Celsius. You know that water boils at 100 degrees Celsius, right? So, but this happens only at a single pressure.
Atmospheric pressure.
Atmosphere pressure, right? So water boils at 100 degrees Celsius at an atmosphere pressure of 101.3. But the boiling point, so this is basically a boiling point only, or a vaporization point. But once we drop the pressure, once we go to a higher altitude, the ambient atmosphere pressure decreases. So at that time, the corresponding temperature at which the water boils decreases, right? So that is basically we are going down the vapor dome from this particular point to down. So corresponding to a saturation temperature, there will be only a saturation pressure.
Okay, sir. Sir, give briefly on phase and compound in Gibbs phase rule. A plus P equal to C plus T.
Yeah, just 1 second. Is my screen visible or not?
Screen not visible.
Okay, just give me.
Visible, sir.
Is it visible now?
Visible.
Okay. Yeah. Right.
Sir, briefly on phase and chemical components.
Yeah. Yes. So the Gibbs phase rule, right? Okay, just 1 second. So for non-binary cases, we can write P plus F is equal to C plus 2. P is the number of phases. F is the degree of freedom or the number of state points required or the properties required. C is the components. So here in the case of steam, number of components and superheated condition, number of components will be equal to 1, and superheat value will be the phase, it will be in vapor. That's a single phase, that will be 1. Now you have to calculate the number of degrees of freedom or the number of properties required to define a state point. So that will be F is equal to 3 minus 1, that is 2. So number 2 state points will be required.
Okay, sir. My doubt is in component, why you would not take hydrogen and oxygen separate?
No, it's a ideal substance, right? So the hydrogen and oxygen are not present independently in this one. So hydrogen, this is a compound. They to combine together, there will be a bond formation energy, and that will be and this exists as a stable component. H2 and H2 plus O2 combine together to give H2. It exists as a stable compound, and in that case, you can't distinguish between the individual elements that is present in this compound. So it's not a mixture; it's a compound.
Okay, sir.
So that is
Got it.
that is a basic distinction that you have to make. If it was a
Got it.
mixture, you have to consider the number of components in accordingly. Or in case of alloys, also you have to. I'm not sure about alloys, but in case of mixture, you have to take the components separately.
Yes, sir.
Yeah. So that will give the number of free degrees of freedom is equal to 2. Yeah.
Okay, sir.
So using this, we have to calculate. I had to give the values for the HF and HFG as such straight away. So in the software which I'm currently using, I have these values separately. I'll mention that the HF, that is the enthalpy corresponding to the saturated fluid, that is equal to 225.9 kilojoule per kilogram. X in this case is 0.9 given, and then HFG, that is the enthalpy of vaporization corresponding to the pressure of 15 kilopascal. We can get it as 2372.3, and the corresponding enthalpy of the state point H2 will be equal to 2361.1 kilojoule per kilogram. So we know the enthalpy at the state point 1 and enthalpy at the state point 2. So that is first step. We have to we have to determine the magnitude of enthalpy, specific enthalpy in terms of kilojoule per kilogram. So H1 and H2, you got it straight away. Now we have to calculate the kinetic energy and the potential energy differences that happens between the inlet and the exit. That's straightforward. In terms of kilojoule per kilogram, if you write kinetic energy, can be written as V squared divided by 2G. So basically delta K. So in the previous case, enthalpy difference could be written as this 3248 minus this H1 minus H2. H1 minus H2, we calculated that will be equal to 8. It's minus 87.34, right? Sorry, H2 minus H1. Sorry, you denote everything from output minus input. So it will be minus 887.39 kilojoule per kilogram. So kinetic energy delta K could be written as V2 squared minus V1 squared divided by 2G. Everything is given straight away. The input velocity is 50 meter per second, output velocity 180. You substitute that and we'll get 180 squared minus 50 squared divided by 2. Why am I writing it as G? Sorry, there is no G here. The unit I'm trying to write is kilojoule per kilogram. There is no G here. So if I divide it by G, then you can get in terms of meters or the head that is associated with the kinetic energy ratio. That will be 14.95 kilojoule per kilogram. And then potential energy G into Z2 minus Z1, that will be equal to 9.81 into 6 minus 10. That's given straight away. Given in this problem, that is minus 0.04 kilojoule per kilogram. And that's very straightforward. You just substitute the value straight away. The change in the potential energy will be equal to G into the change in the altitude. And kinetic energy change could be written as V2 squared minus V1 squared divided by 2 straight away in terms of kilojoule per kilogram. And enthalpy is the main component that we have considered. And the other two components of the kinetic energy and potential energy are very negligible compared to enthalpy. So usually in these kind of problems, we consider we neglect the kinetic energy and the potential energy, and we represent the work done in terms of using the steady flow energy equation in terms of only the enthalpy change in the process. If you need to be accurate, you can account for these two values as well. Yeah. So that will be the first part of the problem, and we need to calculate the work done per unit mass of the steam, and we use steady flow energy equation in this process. So this is a steady process. So what we could do is a d system divided by dt could be written as E in minus E out. This is rate of energy transferred by work, heat, and the flow. And this is the rate of change of internal energy, kinetic energy, and potential energy. This is the steady flow energy equation. So this is a steady process. So this will become equal to 0. Therefore, only E, the input energy, input power, and the output heat transfer rate comes into picture. So we can write it as E dot 1 equal to E dot out. And this energy balance will give us how much. This is an adiabatic process. There is no heat transfer in this process. This will give how much work is transferred from the turbine in terms of kilojoule per kilogram. So how can we write it? The steady flow energy process could be written as m dot into enthalpy, specific enthalpy V1 squared divided by 2 plus GZ1 plus Q1 plus W1 equal to W2 plus Q2 plus m dot into H2 plus V2 squared divided by 2 plus G into Z1. Z2, yeah. So we can actually remove this Q term. It's mentioned it's an adiabatic process. There's only work done in this process. So work is done by the system, so it's positive. So W2 minus W1 will be a positive quantity. You can consider it as net work done in the process. That will be a positive quantity out of it. So we need to calculate delta W. And for that, we take this particular term, this particular quantity to the left-hand side, assuming there is no loss of the mass in the process, assuming that the continuity remains the same. So m dot 1 equal to m dot 2, there is no branches or no loss of fluid happens in this process. So we can assume m dot 1 equal to m dot 2, and that will be equal to m dot, we can write it as this one, into H1 minus H2 plus V1 squared minus V2 squared divided by 2 plus G into Z1 minus Z2 equal to delta W. Z1 minus Z2 equal to delta W. So yes, we need to calculate the work done per unit mass. So we take this m dot to the right hand side. So work done
specific.
Yeah, specific work. H1 minus H2 into V1 square minus V2 square divided by 2 plus G into Z1 minus Z2. So we have already calculated these values, but only thing is that in the reverse manner. So we just put a minus sign and use the values that are present already in the previous case, and we'll get it to be around 872.48 kilojoule per kilogram. So that's straightforward. And now the last part is very straightforward. We need to calculate the mass flow rate of the steam, mass flow rate of steam for a 5 megawatt plant. So mass flow rate of steam is equal to W out divided by work divided by this one, delta W divided by m dot, the specific work. That will be equal to 5 into 10 cube divided by 872.48. So this is megajoule. So in terms of kilojoule, kilowatt, you just multiply it by 10 cube.
5.73
Yes.
kg/s. Okay.
Yeah, so this is a problem that use the steady flow energy equation to calculate the work done per unit mass for this case, and then using the total power that is generated by the steam turbine, we have calculated the mass flow rate of the steam. And
Sir,
how
in
to
Delhi,
arrive at the steady flow?
how
Yeah,
much marks, sir, in offline exam of NPTEL? 5 mark or any?
that you need to actually contact the faculty. But
Mhm.
they would actually announce it prior to the exam. Uh, so we need to look into it. Currently,
Okay.
I do not know it.
Okay, sir.
Okay. If any doubts, if no doubts, we can move to the next problem.
Yes, sir.
So yeah, it's a multiple choice question. Just look into it, straightforward one.
Three.
Yeah, when can we consider that there is no energy generation?
Option
Energy supplied.
three.
Check it
Three.
once.
Um,
Energy supplied to the system is equal to the energy rejected by the system. Rate of change of energy of the system is zero. Energy interaction of the system with the surroundings is only through heat and work. The process is not a cyclic one. So option 3 is wrong actually. That doesn't take into account the flow work or the enthalpy that is present in the case of steady flow case. So we can move straight away. The process is not a cyclic one. It's got nothing to do with it. Energy supplied to the system is equal to the energy rejected by the system. This can be considered if and only if the process is steady. Yeah, this process is steady. And rate of change of the energy of the system is 0. It doesn't say anything. Rate of change of energy, that is a transient component. If the transient component is 0, it doesn't mean it doesn't say anything about the energy generation. So, so this is also wrong. So basically, all the 4 options that are given are kind of wrong. And can we consider there is no energy generation? So if there is no energy generation, the Qgen term will be equal to 0. If there is no internal sources of energy production, just like electrical resistance heating or a chemical energy, chemical reaction resulting in a enthalpy of reaction, that will be rejected out of it. If none of that happens, then we can assume that there is no energy generation. So given the 4 options, the only one which comes close is the option A, if the flow is steady.
Steady flow energy. Sir, actually, in conservation of energy, energy in minus energy out plus energy generation inside the control volume equal to rate of change of internal energy.
Yes, yes, yes.
But during steady state, rate of change of internal energy equal to 0. Then how the energy generation? Energy out minus energy in.
That will be equal to energy out will be equal to energy in if there is no energy generation.
If in option 1, it also mentioned that in a steady condition, then valid.
Yeah, if this is steady, we can ignore this particular term. So if there is no heat generation, in that particular case, this will
Out
be equal to
minus
this.
in.
Yeah. So out of
Out
the
equal to
4
in.
options, only this option is nearby correct, but none of the 4 options are fully correct. So I just want to give a case where multiple choice questions can be like this. Okay.
Next question, sir.
Yeah, yeah. Look into it.
Uh, 1 and 4.
Check it once.
Yes, sir.
Yeah. For the generalized first law of a non-cyclic process, which of the following statement is correct? Heat and work are path functions individually, but their difference is a property of the state. Yes, this is right. Q is equal to U plus W. Q and delta does not depend on. These are path functions. This meanwhile their difference Q minus delta is the internal energy, that is property of the system that depends upon only on the endpoints, end state points. So option 1 is right. Then we move to the option 2. Internal energy is an inexact differential, whereas heat and work are exact differential. It's wrong. Sum of heat and work gives the total energy of the system. Total internal energy of the system, sum of heat and work. No, that's wrong. It's a difference between these two that gives the total internal energy of the system. And heat and work are inexact differential, whereas internal energy is an exact differential. Yes, that's right. So you can write it in terms of exact and inexact differential, where you can define one property as the derivative of the others multiplied by the change in the base property. Like that, you can write in terms of exact and inexact differential. Yes. So option 4 is wrong. Option 4 is right and option 1 is right. So other two are wrong. Now look into this problem. This is a Carnot heat engine based one, straightforward one. Obtain the thermal efficiency of the Carnot cycle and the amount of heat rejected to the sink per cycle.
A formula like thermal efficiency is 67.24.
Yes, right. You're right. Now calculate.
67.24% thermal efficiency and heat reject 168.3 kilojoule.
Yes, nearby. It's nearby that only. A Carnot heat engine. I'll try to solve it quickly. A Carnot heat engine shown in figure. I'll draw the figure. If the figure heat engine reservoir at 652 degrees Celsius and it's at 30 degrees Celsius. Lower is 50 degrees Celsius. Let's work connect out. It rejects heat to a low temperatures heat sink, and the heat source is at 652 and heat exchange is 500 kilojoules. We need to calculate the thermal efficiency of the Carnot engine and the amount of heat rejected to the heat sink per cycle. So efficiency of the Carnot engine will be written as 1 minus PL because it's reversible. Carnot, it's the highest efficiency, so you can denote it in terms of the temperatures that is associated with it as straight away. And then so that is 1 minus 303 divided by 652 plus 273, and that you'll get as 67.2%. And the second one, straight away efficiency can be written in terms of the work divided by the Q input. So that will give the work net is equal to efficiency into Q in. Q in is 500 and you'll get it as 336 kilojoules. And the heat rejected Q out to Q in minus work out. So that will be equal to 164 kilojoules. Straight away you can calculate. Yeah. I guess it's straightforward. Now we can move into the next problem. Because we need to finish within another 15 minutes. I have a couple of problems as well. So yeah, just look into it. It's a problem on the entropy change of air. During this process, air is compressed from an initial state of 100 kilopascal and 70 degrees Celsius to a final state of 600 kilopascal and 57 degrees Celsius. Determine the entropy change of air during this compression process by using a property values from the air table and average specific heat. Uh, So basically what we are trying to see is whether using an average specific heat will be throwing in a huge error compared to using the actual property values that you get from this air table. So this requires you to brush up into the entropy change formula. For an ideal gas, the entropy change could be written as the change in entropy of the starting and the end process end state points minus R into the pressure variations.
Minus
So
CP.
yeah. So what we can so one way is that you can directly calculate the entropy from a table, property table, and R from the property table as well at these corresponding temperatures and the pressure. So R is a constant for air, so that is 0.287 kilojoule per kilogram Kelvin, and correspondingly use the pressures and calculate the volume. From a state, I just want to show the variation between these two processes. So from the property plot, property values, S2, the entropy at the state point 2 was 600 kilopascal and 57, it's 1.79 kilojoule per Kelvin. And then S1 is S1 is 1.668. So this is specific entropy. The unit will be equal to kilojoule per kilogram Kelvin. Kilojoule per kilogram Kelvin. So this will be specific entropy at this will be T1 comma P1 and this will be T2 comma P2 from the property table. So R will be 0.287 kilojoule per kilogram Kelvin for air. So you substitute that straight away and put the pressure points 600 divided by 100. So that will be giving you a change in entropy during this process as minus 0.3844 kilojoule per kilogram Kelvin. So this is very much possible, the negative value, because we are actually considering the change in entropy during the process. We are not considering the change in entropy of the universe. So so the change in entropy of the universe will always be positive. It can't be negative. So if it is a ideal reversible process, it will be equal to zero. The entropy of the entropy change of the universe will be equal to zero. But if it is a irreversible process, it's a instantaneous spontaneous process. Delta entropy change of the universe will be greater than zero. That is the entropy change of the universe. But here we are just calculating the entropy change of the process. It doesn't mean the entropy change of the universe. So this can very well be negative as well. This is using the property plot straight away. Now, the other way you can calculate is using an average specific heat delta S. This first term, if you do not have a property table with you, you can actually calculate an approximate value as Cp of
Long
ln
T2
P1 minus Res, ln of P2 by P1. So the CP, you take an average CP between these two state points, and I have used 1.006 kilojoule per kilogram Kelvin, and correspondingly put the temperature T2 is 330 Kelvin, and the temperature T1 is 290 Kelvin, and the same R and P2 P1 values on the right hand side, and you'll get the value of delta S to be somewhere nearby. So uh, even if you do not use the same entropy values, specific entropy values as from the table, if the temperature variation between the initial and the final points are very less, what you can say is that the entropy change of the process is you can get within the vicinity of the actual value of the entropy change. So even if you do not have a table as such, you can calculate it using this second pattern, second formula, Cp ln of T2 by T1 minus of R ln of P2 by P1. Any doubts?
No, sir.
Now we can move to the 10th problem. Next problem. Consider the steady heat transfer through a 5 by 7 brick wall of a house of thickness 30 centimeters on a day when the temperature of the outdoor is 0 degrees Celsius and the house is maintained at 27 degrees Celsius. The temperature of the inner and the outer surface of the brick wall are measured to be 20 and 5 degrees Celsius respectively. And the rate of heat transfer through the process is through the wall is 1035 volt. We need to determine the rate of entropy generation in the wall and the rate of entropy generation associated with the heat transfer process. Hello, am I
Yes, sir.
audible?
Yes, sir,
Yeah.
audible.
So I had just rushed through it because we do not have much time left. Yeah,
Okay, sir.
I'll try to solve it straight away. And this is a steady heat transfer process through a 5 by 7 brick wall cross section. And the thickness is 30 centimeters. And the outside temperature is 27 degrees Celsius, and the inside the temperature of the inside temperature is 27 degrees Celsius, and the outside it is at 0 degrees Celsius. Inside wall will be at 20 degrees Celsius, outside wall at 5 degrees Celsius. This is indoor and the outdoor condition. And the heat transfer in this process is 1035 watt. We need to calculate the entropy generation in the wall and the rate of entropy generation associated with this heat transfer process. Yes, for that we need to have the entropy balance, rate of entropy balance equation. The first part we need to calculate the entropy generation in the wall. Rate of entropy balance for the brick wall control volume. So if you take a control volume around this brick wall, what we can write is that entropy in minus entropy out rate by heat and mass, net rate of entropy transfer by heat and mass plus entropy generation rate of entropy generation is equal to rate of change of the entropy within the control volume. That will be equal to 0 since it's a steady process. So the entropy generated within the wall, within the brick wall, will be equal to the change in the entropy due to entropy transfer due to heat and mass. Basically, entropy at the inlet wall could be written as we can write it as question is equal to S out minus S in. So this is a steady process. The incoming heat will be going out as well. So there is no heat generation as such in this process. And it's a steady process.
0.19.
Yeah, right. So this will be equal to Q divided by T
5 plus
out.
2,
Yeah, minus delta Q divided by T in. So we are taking the magnitude of it. So Q heat transfer is 1035 watt divided by temperature associated with it is 278 at the output at the outside area of the brick wall. So the flow happens from the inside to outside. So we are considering out to be this wall, this particular wall, and inside will be Q divided by 2293, and we'll get it to be 0.191 watt per Kelvin. So that is rate of entropy balance for the brick wall. So this is the first part, and the second part we need to calculate the rate of total entropy generation associated with this heat transfer process.
into volume.
You need to get in terms of watt per Kelvin only, but just think about it.
So 0.2.
No, there is a slight difference because we have considered the first part of the problem with wall as the control volume. And there we have taken into consideration the surface temperatures of the wall. And that will help us to get the entropy generation in the wall. The next one is the rate of total entropy generation associated with this heat transfer process. So in that particular case, we have to take the entire control volume, entire control volume that includes the inside and the outside spaces as well, the zones as well. So in that particular case, the control volume and analysis will be slightly different. The control volume under consideration will be including the outside spaces as well, where the temperature will be 27 degrees Celsius and the outside temperature will be 0 degrees Celsius. So the heat transfer has to, the entropy calculated has to take into account these two temperatures. Therefore, if you take the total thing as the control volume, we can write the S in minus S out plus S gen is equal to D system divided by dt. This is equal to 0. Entropy generated, we have to determine this process. So entropy generated will be equal to S out minus S in. So the only thing that is different in this case is that the Q remains the same. The temperature, the higher temperature sink as well as a higher temperature source and the lower temperature sink will be different in this case. The reference temperatures will be different for the entropy calculation.
0.344.
So, yeah, right. That's correct. So it will be 273 degrees Celsius, and here it will be 300 degrees Celsius corresponding to 27. So that will give us 0.341 watt per Kelvin. So that is a basic difference that that needs to be accounted while solving these kind of problems. So you need to look into the problem specifically. And see what exactly the question says, whether you need to calculate the entropy generation within the wall or the total entropy generation within the process. So if you want to calculate only the entropy generation within the wall, you only take into account the wall surface temperatures while calculating the inlet and the outlet entropies. While at the same time, if they ask for the total entropy generation associated with this process, you need to take into account the higher temperature source as well as the lower temperature sink for calculating the entropy generation for the process.
Yes, sir.
Okay. Right. Now we can move into the last problem. It's a multiple choice question. In the adiabatic expansion of a wall, the temperature changes from T1 to T2. The entropy in this case will increase, remain unchanged, decrease, may increase or decrease depending upon the right. So what we could say is that delta S is equal to entropy change rate of change of entropy is equal to S2 minus S1, that is outlet minus inlet, plus entropy generation. So in this case, and we need to see that there is no entropy generation as well. So that is a given in this problem. No, then only this will be valid. So this can be assumed to be reversible and reverse. It's I didn't mention it as a reversible adiabatic. So if it was a reversible adiabatic, then the entropy remains. If it was a reversible adiabatic, delta S would have been 0 and we could have written S2 is equal to S1. But in that case, there is no entropy generation as well. So we need to specify this is an adiabatic expansion process plus no entropy generation is happening in this process. Then only we can say that the S2 minus S2 is equal to S1. So this is a reversible adiabatic
Sir, one
isentropy. Right. Yeah. Tell me.
Sir, in both liquid and the gas, if in question mentioned that the
Uh,
wall is adiabatic, then we cannot
uh,
apply Q equal to MC delta T or Q equal to 0 na, always for reversible, sorry, for adiabatic wall or insulating wall.
for the gas, it will be different, right? The gas, there will be mixing enthalpy and other terms that comes into picture. So mixing entropy difference, right? One particular term will be there, additional term will be there.
Okay. For
But for
liquids,
the liquids, you can straight away write it's incompressible, right? So the we can express in terms of temperature or pressure. So it will be m into Cp into ln of T2 by T1, right? So that formula you can straight away take.
oh, okay, sir.
Just give me a second. I have that in my backup slide.
Okay.
Yes. So,
Sir, for engineering thermodynamics, PKNAG is sufficient for GATE.
uh, you can actually look into Senjal as well.
For numerical,
Yeah, you can try Pikenak, we can try Senjal. Both these books are good enough to get the problems done.
okay.
Okay. Yeah. So this is you mentioned about liquids, right? For the entropy change.
Last year in GATE, question was asked though, for liquid, the wall is adiabatic side or insulating side, the
Uh-huh.
two temperatures are given, sir, T1, T2. So
Uh-huh.
I calculated
Uh-huh.
Q equal to MC delta T. Though
Uh-huh.
it was wrong because they mentioned insulated. I did not see the term. So Q equal to 0.
Yeah, Q is equal to 0. Yeah.
For insulating and adiabatic, both the cases, no, sir, for liquid and gas.
In insulating means it will be adiabatic only. There will not be heat transfer.
Uh, and adiabatic also Q equal to 0 for both liquid and gas.
For liquid and means it has got nothing to do with whether it's a liquid or gas, right? So adiabatic means that it's a boundary condition. So the there will not be heat transfer that happens between the outside surroundings as well as the inside zone through the boundary. So it has got nothing to do with whether it's a liquid or a gas. So
Okay, sir.
I thought that your question was on the entropy formula for the liquids or solids. So it's it's average C into ln of T2 by T1, the thing that we have just told, like
Uh,
yeah. Yeah, so in this case, it's an adiabatic case. So what you can write is that this will be delta Q divided by T. It will be equal to 0. No heat transfer happening across the sides, the inlet and the outlet. So it will be Q by 0. And since we have mentioned that there is no entropy generation that is given in the problem given. So if that is the case, you can write it as total entropy remains a constant. So delta S is a delta S will be equal to 0, and total entropy remains a constant.
Mm.
So this is inlet and outlet. So S at a future time and S at a previous past time, that will remain a constant if this is the case.
Okay, sir.
Okay. Yes, that completes this. Yeah.
Next problem section when will happen, sir? In
We will
February
have
in GATE exam.
We will have our sessions on every Monday at the same time. Sorry, every Sunday at the same time.
Okay.
Yeah.
Next Sunday it will be GATE, I think.
Oh, it will be GATE. Okay. But I am a PhD student, right? So I have to manage my time accordingly. That's why I had to. Yeah, if the PMRF the NPTEL authority say that we can't take a class at that time, yeah, we will force to change. We'll force to give it another time. Yeah.
Okay, sir. Sir, this
So otherwise the
course,
class will go on.
this course, do not provide by IIT Delhi, provided by IIT Guwahati, I think, thermal and
Yeah,
basic
it's like
and
yes, yes. This course is provided by uh, professor uh, professor from IIT Guwahati.
uh,
Yeah,
Pranav sir.
yeah, Pranab Kumar Mandal. His name is
Mandal sir.
Pranab Kumar. Yes. So, but actually, my tutorial sessions are actually kind of independent from what he'll be discussing in the uh, course website. So the kind of assignments that they give in the course website is slightly different from the questions that I am discussing right now. So this will help you to solve a few of those problems. But
Yes, sir. Sir,
the
please
assignments.
bring related to GATE also third wise.
Yeah, these kind of problems can help you for the gate.
Uh, uh. In further
Right.
sessions also, sir. In
Yeah, right.
power plant, these are.
Yeah, but we have to actually follow the structure that is given in the website, right? So they will
Syllabus.
be having particular lectures in this particular week, and we
Weeks.
have to follow the same structure. Yeah.
Okay, sir.
Yeah, that completes the problem solving session for the week. If you have any doubt, you can post that in the course website forum. So the TAs for the course will be answering it straight away.
Sir, this
And
video will available in the course section.
yeah, it should be available by tomorrow. The NPTEL authorities will share the link with you where
Okay.
you can actually access these videos as well as the slides.
Sir, is IIT Delhi provide any course like ANSYS or computational or the hands-on practical section online? ANSYS.
Uh, I not, but see, assignment, it's not an year-long course, right? Occasionally, what happens is that there will be some departments they will be offering it as a workshop or kind of like a short duration course, maybe for a few days. But it doesn't happen the year long. So
For 1 month at least.
I don't think so. Uh, Actually, here you would not require a course from IIT Delhi as such. You can, if you want to get to know about more this about these items, you can actually search in YouTube. There are so many other sessions that are available. It need not be a paid course as such. It will be openly available videos. Uh, that will be a session by maybe PhD students who will be from IIT or from some foreign universities as well. You can use that. You need not actually. Okay, you need a certificate for that course or what?
Certificate means central government
Oh,
on
certificate
ANSYS.
course. I don't think IIT Delhi is offering any.
Yes, sir, not offering.
Yeah. So, but other than that, there are some paid courses that are available in internet. You can try that. But IIT Delhi, I don't think so. I'm not aware about it.
Okay, sir.
Yeah. Any questions regarding the session, regarding today's problems?
No, sir.
Then we can meet next week with the next week lectures.
Okay.
The lectures are already available in the course website. So I'll come with another set of tutorial problems based on the next week lectures.
Sir, next week, what
Thanks.
will the syllabus? In which topic you will make the questions?
Yeah, so I can give you that. Give me a second.
We'll prepare from now also for
It's
that topic.
steam. The topic is steam power engineering. Basically, it comprises of power plant applications of first and second. Rankine cycle applications of first and second law for this power plant cycle, and ideal power cycle limitations, then the actual power cycle. Yeah, basically a steam power plant.
Steam power. Okay.
Yeah.
Okay, sir.
Yeah.
Thank you.
Okay. Thank you. Thank you.
Can you leave, sir?
Yeah, I can.
Happy Republic Day, sir.
Yeah, happy Republic Day. Yeah, you too.
Good night, sir.
Yeah, good night.